All right. Well, thank you for joining and listening. And it's my pleasure to talk a bit about repurposing, both at a high level and somewhat general terms, before diving into a case study. What I'd really like to do is kind of set the stage for a lot of what we're going to see today and how we think about repurposing more generally. The high level question is, how do we end up repurposing a drug? And I think at this very high level, there are more or less two very general categories of approaches. I divide them into what you might call the rational and the empirical. And if we move on to the empirical, there's one that's really touches on the heart of what we're really interested in today, or more generally, which is, can we use real world data to infer that a drug should be repurposed for a particular disorder? And I'll give you one example of that through this case study where there seems to be a very strong signal that yes, absolutely you can. And this leads to a natural question, which is, once you see a signal like that, how do you move forward? How do you actually move to get something on label at that point? And is it sufficient to have just that real world data to do it? In general, there are other approaches on the empirical side. You're going to see examples of that. There's precision disease modeling. So in precision disease modeling, it really begins with the patient and the construction of a precision disease model. It could come from the patient themselves in the sense that this model could be their own tissue or reprogrammed versions of their own tissue, but it is a physical avatar that represents their disease. And of course, it could be an animal model, like it could be a fly, a fish, a worm, a rat, as long as it in some way captures or reflects their disease. And once you've got that model, you can combine it with an assay to interrogate that model, or some sort of experimental system that observes the activity of the disease in that model. Once you've got that activity, that signature, if you will, that's the phenotype. And the goal at this point is to start combining the model with other drugs to see if anything out there reverses that phenotype or rescues it. And once you've got that, you can start testing that model against lots of drugs. And hopefully something out there that you test rescues the model. And further, that what rescues the model also rescues the human, which may not be the case always. There's a big gap between a cell and a human being. That's something else we can touch on today. But it's a starting point. If it doesn't rescue the model, it sort of hurts the chances that it's going to rescue the human. But that's not always the case either. So this is one way of looking for potential candidates for repurposing. In addition to, for example, mining out medical records or patient histories to see if there's something in there that is suggestive of benefit. Again, one benefit of this approach is you can just test a lot of drugs on a model. Now, when we talk about the rational approaches, there's sort of an encapsulating approach to this, which is artificial intelligence. And by rational, I mean trying to predict, based on the known root cause of a disease, what might be beneficial. So if there's a core molecular impact that we're dealing with, maybe there's a way to address that core molecular impact. So if something has become underactive, maybe we can predict what will activate it. If something is overactive, maybe we can predict what will inhibit it. So this is how we can use these more rational approaches to repurposing. And artificial intelligence is a pretty broad term, but in almost any incarnation, it's been fruitful in providing suggestions about ways to do exactly this once the root molecular cause of a disease is understood. I'll talk about one particular platform that we use that we built at my institute for doing this. It's called Canron, but this is part of a larger consortium project from NIH called the Biomedical Data Translator. So this is one interface to this large consortium. And just to give you a sense of what it is and how it thinks and what it can do, it's really a fusion of logical reasoning and as much biomedical knowledge as anyone can get their hands on, or any one machine, really. And in broader terms, it's what you get when you have a fusion of old school logic with high-speed automated reasoning to achieve superhuman-like deduction with what we hope is clinical insight. And once you have an artificial intelligence agent like this, you can ask it very high-level questions. You can say, what may be a treatment for this particular disease here? And it can try to hypothesize that or search in parts of the literature that aren't typically searched or databases that aren't typically known for such treatments. It can try to stitch things together to logically infer the existence of a treatment that somebody might not have thought of otherwise. Or, as is more commonly the case when we use it on specific patients with rare diseases, we'll ask a very specific molecular question. We will say, what's an inhibitor for X? Or what could be an inhibitor for X? Or what's an activator for X? We might be trying to perturb just one thing in that patient, at least one core thing. So how do you do this? How do you build up a tool that can answer questions like that? Well, you start by reading all of PubMed, all 30 million papers. And luckily, we don't have to do this as human beings. We can let robots do this for us. So there's ways to use natural language processing, as tools like SendMedDB have done, to digest essentially every abstract in PubMed for us. And we leverage that, plus at this point, literally hundreds of other databases that have been built and compiled by this Translator consortium at NCATS to give us clues as to what might be beneficial for a patient. And now I'll talk about how that's collided with real world data in the context of one disorder. So this particular disorder is hyperactive KCNMA1. This is a potassium channel in this case. And you may have seen this particular patient in the public before. There's been a lot written about her in the New York Times. An episode of a show on Netflix has covered this particular case, but she was in fact the first patient in the world to have a hyperactive, or known to have a hyperactive potassium channel like this. And so once it was a confirmed gain of function, the question was, how do we address this? Can we find some inhibitor for it? Because what it leads to is on the order of hundreds of cataplexic episodes per day. Which is just heartbreaking to watch, and really prompts the question: what can we do about this? Is there any way to help with these episodes? And initially, when this was dropped into an early prototype of Medicadron, it actually gave a number of answers, and the answer it shot right back was methamphetamine, like literally the illicit drug, crystal meth, as an inhibitor for this channel. And while it may in fact be an inhibitor for this channel, we immediately sort of pushed it to the side because we thought, well, no one would prescribe this. It seems crazy to do that. It also reported that there were some venoms and toxins which were exquisitely selective inhibitors for this channel. And we even thought, well, maybe we can use these as very targeted therapies for this disorder. With partners, we had comprehensive chemical screens like I described earlier, where we literally tested every single existing drug against this channel and got some hits, but none that immediately got us really excited about what to do in terms of treatability. And part of that was because in the intervening time from when we started those queries to launching the screen, more patients began to show up. And when I talked to one of those patients' dads on the phone, he said, oh yeah, we've actually got this thing under control. We've got it pretty successfully treated. And I said, what? How on earth have you got this under control? Because we've been trying very hard at this. He goes, oh, it's just amphetamines. So his son was on an ADHD drug, which happened to be listexamphetamine. And it seemed to be a very effective treatment for this particular disorder. That's why we realized you have to think in terms of structural similarity sometimes when you repurpose too. You might get a clue that one drug works, but that drug might be out of scope for some reason, as it was in this case. And so it's important to ask, well, is there another similar drug that would have worked or could also work? And in this case, if you look at the structure or structural differences between methamphetamine and amphetamine, there's not much. We're talking about a methyl group. So this wasn't a big shift. And in fact, not only did the same drug work for the original patient we were in touch with, because she called to tell me that it worked, it's now working for at least 5 more patients around the world. And in fact, what they're reporting back is that it seems that almost any amphetamine will work. So, this really gets us thinking. The signal might not be just one drug out there in the real world data. It could be hinting that a class of drugs is actually what's really going to work. And if we want to mine out real world data to find this in a more systematic way, we've got to be able to anticipate that and look for it. And also look at all the other things that any one individual drug might do. And again, this is an area where once the real world data exists, we can combine it with AI to find exactly that. Next step in this case, of course, is do a clinical trial. Let's see if we can get something on label here. And what's striking to me here is a broader question, which is, okay, there's now multiple, like every patient that has done this is now experiencing a dramatic reduction in episodes, often a total cessation of these episodes. So there's really no doubt in anyone's mind at this point, the clinicians or the patients, that this class of drug seems to be working. So the real question is, how do we, and then there's that real world data, and then there's the underlying data from the biology saying this would probably work too. And what I'm wondering is, and this is a question really for discussion, is at what point, do we have a lowered threshold for a rare disorder for putting something on label? Because it's going to be a big lift to do a clinical trial. We're going to try to do it because it's important. But it really gets me wondering, is there something easier we can do? Is there some way to capture the inherent confidence we've got amongst the patients and the clinicians and use that to really drive a labeling decision? And with that, I thank you, and I look forward to discussion.